Earth has an expiration date, not billions of years from now when the sun swallows us, not millions of years from some asteroid impact, but in roughly 1 billion years, our planet will lose something far more fundamental than land or water. It will lose its oxygen. The air we breathe, the atmosphere that sustains every animal, every plant, every breath you've ever taken will vanish. Earth will become a world where nothing that breathes can survive. This isn't speculation. This isn't maybe. Scientists have calculated when and how it will happen, and understanding this timeline changes everything about how we see our place in the universe and the extraordinary gift of this moment we're living in. If understanding Earth's ultimate deadline sounds worthwhile, a quick subscribe would mean the world to me. And drop a comment letting me know where you're watching from. Let's explore the day Earth stops breathing. The story of how we know Earth will lose its oxygen begins in 2021, when a team of scientists published a study that sent ripples through the scientific community. Kazumi Osaki from Toho University in Japan and Chris Reinhard from the Georgia Institute of Technology ran complex computer simulations modeling Earth's atmospheric evolution over geological timescales. They weren't looking at what might happen in a few centuries or even millennia. They were projecting forward hundreds of millions of years, watching how Earth's atmosphere would change as the sun aged and grew brighter. What they found was startling in its clarity and inevitability. Earth's oxygen-rich atmosphere, the defining feature of our planet for the past 2 billion years, will persist for approximately another billion years. Then, over a geological eye blink of perhaps just 10,000 years, oxygen levels will plummet. The atmosphere that took 2 billion years to build will collapse in a tiny fraction of that time. This wasn't just theoretical speculation. The researchers used everything we know about planetary science, atmospheric chemistry, solar physics, and biological processes to create their models. They accounted for how the sun's luminosity increases over time, how this affects Earth's temperature, how temperature affects chemical weathering of rocks, how weathering affects carbon dioxide levels in the atmosphere, how carbon dioxide levels affect photosynthetic organisms, how photosynthesis affects oxygen production. All of these systems are interconnected. Change one and everything else shifts. The model tracked these interconnections forward through deep time, and every simulation, no matter how they adjusted the variables within reasonable ranges, pointed to the same conclusion. In roughly 1 billion years, give or take a few hundred million, Earth's oxygen levels will crash. The timeline is staggering to contemplate. 1 billion years. That's 70% of the time that complex life has existed on Earth. It's longer than the entire history of animals. When oxygen levels begin their final decline, the distance in time from that moment back to today will be greater than the distance from today back to the first sponges. We're talking about deep, profound stretches of geological time. But in the context of Earth's total lifespan, it's the final act. Earth formed 4.5 billion years ago. The sun will expand into a red giant and likely engulf Earth in about 5 billion years. So, this oxygen loss happens in that narrow window before the final curtain. Earth will spend its last billion years as a world without oxygen, a return to the conditions that prevailed for the first half of its existence, a planet where complex life cannot persist. But what is oxygen really? Why does it matter so fundamentally? We breathe it constantly. Every few seconds, you inhale. Your lungs extract oxygen from the air. Your blood carries it to your cells. Your cells use it to burn fuel, to generate energy, to power everything your body does. Without oxygen, this process stops. You suffocate. Not because you can't breathe in, but because your cells can't generate the energy they need to function. Oxygen is the key that unlocks energy from food. Without it, complex life as we know it cannot exist. This is why oxygen matters, not just because we need it to breathe, but because it enables a type of metabolism that's far more efficient than anything that works without oxygen. Let's talk about what our atmosphere actually contains. When you take a breath, you're inhaling a mixture of gases. About 78% nitrogen, about 21% oxygen, about 1% argon, and tiny amounts of other gases including carbon dioxide, methane, neon, helium. Nitrogen is the dominant gas, but it's mostly inert. Your body doesn't use it. It goes in, it goes out, unchanged. Oxygen is the active ingredient. That 21% is what matters for complex life. And that number hasn't always been 21%. It's varied over Earth's history. At times, oxygen levels were higher. During the Carboniferous period, about 300 million years ago, oxygen might have been as high as 35%. This allowed insects to grow to enormous sizes. Dragonflies with wingspans of 2 feet, millipedes over 6 feet long. The higher oxygen levels supported larger body sizes in animals that breathe through simple systems. At other times, oxygen was lower. After major extinction events, oxygen levels sometimes dropped. But for the past few 100 million years, it stabilized around 21%. This is the oxygen level that supports the diversity of life we see today, from tiny bacteria to blue whales, from microscopic algae to giant sequoias, all dependent on this one gas making up 1/5 of the atmosphere. But oxygen wasn't always present in Earth's atmosphere. For the first half of Earth's history, roughly 2 billion years, the atmosphere was essentially oxygen-free. Early Earth was a very different world. The atmosphere was mostly nitrogen and carbon dioxide, with significant amounts of methane. Poisonous to us, perfect for the microbes that dominated that ancient world. These were anaerobic organisms, life that doesn't use oxygen. That actually finds oxygen toxic. For them, Earth was paradise. But then something revolutionary happened. About 2.4 billion years ago, a type of bacteria evolved that changed everything. Cyanobacteria, sometimes called blue-green algae, though they're not actually algae. These microscopic organisms developed a new trick: photosynthesis using water. Previous forms of photosynthesis used hydrogen sulfide or other compounds. But cyanobacteria learn to split water molecules. Water is abundant, oceans full of it. This gave cyanobacteria an enormous advantage. They could live anywhere there was water and sunlight, and when they split water molecules to get hydrogen for photosynthesis, they released oxygen as waste. At first, this oxygen didn't accumulate in the atmosphere. It reacted with iron dissolved in the oceans, forming iron oxide that settled to the ocean floor. These deposits, called banded iron formations, are visible today in ancient rocks. Layers of red iron oxide alternating with other minerals. A record of that ancient oxygen production. For hundreds of millions of years, the oceans soaked up oxygen, but eventually the iron was used up. oxygen began bubbling into the atmosphere, and this triggered the Great Oxidation Event. The Great Oxidation Event, sometimes called the oxygen catastrophe, was the most profound change in Earth's history. It happened over a period from about 2.4 to 2 billion years ago. Oxygen levels rose from virtually zero to a few % of the atmosphere. This doesn't sound like much, but it was catastrophic for the anaerobic organisms that had dominated Earth. Oxygen was poison to them. It destroyed their biochemistry. Most died. Some survived in environments without oxygen. Deep mud, animal guts, anywhere oxygen couldn't reach. These survivors persist today as anaerobic bacteria, but they no longer dominate. The world belonged to organisms that could handle oxygen, that could use it, that could thrive in an oxidizing environment. This opened the door for everything that came after: complex cells, multicellular organisms, animals, plants, all of us. We are the descendants of organisms that adapted to the oxygen world. Our biochemistry is built around oxygen. We need it. We can't imagine life without it. But for most of Earth's history, oxygen was absent, and in the future, it will be absent again. The reason oxygen will disappear is connected to a slow but inexorable change happening to the sun. Stars are not static. They evolve over their lifetimes. The sun is currently about 4.6 billion years old. It's in the middle of its main sequence lifetime, the period when stars burn hydrogen in their cores. During this time, the sun is gradually getting brighter. This isn't something you'd notice in a human lifetime or even over thousands of years. But over hundreds of millions of years, the change is significant. The sun today is about 30% brighter than it was when Earth formed, and it will continue brightening. In another billion years, the sun's luminosity will be about 10% higher than it is today. 10% more energy hitting Earth, 10% more heating. This might not sound dramatic, 10% over a billion years, but the effects compound. More sunlight means more heating. More heating means more evaporation from oceans. More water vapor in the atmosphere. Water vapor is a greenhouse gas. It traps heat. This creates a feedback loop. More heat means more water vapor, which means more heat. Earth's temperature will slowly but steadily rise, and as temperature rises, something crucial happens to the carbon cycle. Carbon dioxide is constantly cycling between the atmosphere, the oceans, and rocks. Plants take it from the air. Animals return it through respiration. Oceans absorb it and release it. Volcanoes emit it, and crucially, chemical weathering of rocks consumes it. When carbon dioxide dissolves in rainwater, it forms a weak acid. This acid reacts with rocks, especially silicate rocks. The reaction pulls carbon out of the atmosphere and eventually deposits it in carbonate rocks. This weathering process is temperature dependent. When Earth is warmer, weathering happens faster. More rain, more moisture, more chemical reactions, more carbon dioxide pulled from the air. Here's where it gets critical. As the sun brightens and Earth heats up, weathering accelerates. Carbon dioxide is pulled from the atmosphere faster. Now, normally, volcanoes would replenish this carbon dioxide. They release it from Earth's interior. But there's a limit to how much volcanoes can emit. And as weathering accelerates with rising temperature, it eventually outpaces volcanic emissions. Carbon dioxide levels in the atmosphere start to drop, and this creates a problem for photosynthetic organisms. Plants and cyanobacteria need carbon dioxide for photosynthesis. They take carbon dioxide from the air, split it apart using energy from sunlight, and build carbohydrates. The oxygen they release is a byproduct. But when carbon dioxide levels drop too low, photosynthesis becomes difficult, eventually impossible. And when photosynthesis stops, oxygen production stops. The oxygen in the atmosphere starts to decline. It reacts with volcanic gases, with methane from anaerobic bacteria that flourish as oxygen drops, with rocks and minerals. Oxygen gets consumed faster than it's produced, and once this process starts, it accelerates. The models show that once carbon dioxide drops below a critical threshold, the oxygen collapse is rapid. 10,000 years or so. That's nothing in geological terms. A blink. The oxygen we've enjoyed for 2 billion years will be gone in what amounts to an instant. And with it goes everything that depends on oxygen. Plants die first. Without carbon dioxide, they can't photosynthesize. Forests wither. Grasslands brown and die. Crops fail. Algae in the oceans disappear. The green planet becomes brown. Then animals follow. Without plants, herbivores starve. Without herbivores, carnivores starve. But even if there was food, the dropping oxygen levels would suffocate them. Mammals and birds go first. They need high oxygen levels for their active metabolisms, then reptiles, then amphibians. Fish in the ocean survive longer, but eventually even they can't extract enough oxygen from the water. The world becomes silent, empty, dead of complex life. Only anaerobic bacteria remain. The organisms that ruled Earth before the Great Oxidation Event reclaim their throne. Earth returns to its original state. An anaerobic world, a world that looks from space much like it did 3 billion years ago. Red and brown and dead to us, but teeming with bacterial life that doesn't need oxygen. Let's walk through the timeline in more detail because understanding the stages helps grasp the magnitude of what's coming. Today, we're safe. Oxygen levels are stable at 21%. Carbon dioxide levels, currently rising due to human activities, will eventually decline naturally as fossil fuels are depleted and weathering processes continue. Over the next few 100 million years, nothing dramatic happens to oxygen. The slow solar brightening causes gradual warming, but Earth's carbon cycle compensates. More weathering pulls more carbon dioxide from the air. The planet stays habitable. Life continues evolving. Species come and go. Continents drift. Oceans open and close. But oxygen persists. This is the safe zone, the long stretch where Earth remains as we know it. Around 500 million years from now, things start to change more noticeably. The sun's increasing brightness has pushed Earth's temperature higher. Carbon dioxide levels have dropped significantly from today's values. They're low enough that some types of photosynthesis start to struggle. C3 photosynthesis, the kind most plants use, becomes less efficient. Plants that use C4 photosynthesis, a more efficient system evolved in grasses and some other plants, have an advantage. But overall, plant productivity is declining. Forests are smaller, less dense. Deserts are expanding. The planet is heating up and drying out. Oceans are evaporating slowly. Water vapor in the atmosphere is increasing. This is the beginning of the runaway greenhouse effect that will eventually render Earth uninhabitable. But oxygen is still present, still around 15 to 20% of the atmosphere. Animals still roam the land and swim in the seas. But the world is changing, becoming harsher, less hospitable. At around 800 million years from now, we reach a critical transition. carbon dioxide levels have dropped so low that most photosynthesis is shutting down. Only the most efficient photosynthetic organisms persist in isolated pockets. Oxygen production has slowed to a trickle. Oxygen levels in the atmosphere are dropping noticeably now, maybe down to 10 or 12%. This is still enough to support some animal life, but it's borderline. Large animals with high metabolic rates are gone. Only small creatures with low oxygen requirements persist. The oceans are becoming anoxic. Without oxygen, different chemistry takes over. Hydrogen sulfide starts building up. The seas turn purple or green with sulfur bacteria. The land is mostly barren. A few hardy plants cling to existence near coasts where moisture is available, but vast regions are sterile, rock and sand, and nothing growing, nothing moving. The wind howls across empty plains. Then, around 900 million years from now, we reach the cliff edge. Carbon dioxide is nearly gone from the atmosphere. The last photosynthetic organisms die. Oxygen production stops completely. And over the next 10,000 years, oxygen disappears. It reacts away, gets consumed by geological and biological processes. The atmosphere becomes dominated by nitrogen and carbon dioxide released from volcanoes, with increasing amounts of methane from anaerobic bacteria. This methane builds up in the oxygen-free atmosphere. It creates a haze. From space, Earth looks murky, red and brown with a yellow haze. Similar to how it looked before the Great Oxidation Event. Similar to how Titan looks today. A world with a thick atmosphere, but no oxygen, no complex life. The transformation is complete. Earth has returned to its anaerobic state, and it will remain this way for the rest of its existence. Another billion years or more before the sun's final expansion destroys the planet completely. What will Earth actually look like during this oxygen-free future? Imagine standing on the surface, though of course no human could survive there. The sky is a murky orange or yellow. The sun, much brighter than today, beats down through a hazy atmosphere. The temperature is well over 50 degrees Celsius, hot enough to kill most organisms we're familiar with. The land is barren rock, red and brown from iron oxides, wind eroded, dry, no plants, no soil. Soil requires organic matter from dead plants and the activity of organisms. Without life, there's no soil, just weathered rock. In low areas, you might find deposits of salts left behind as water evaporated. The oceans are much smaller than today, maybe half the volume or less. Much of Earth's water is in the atmosphere as vapor. The oceans that remain are warm, acidic, devoid of oxygen, purple or green with mats of photosynthetic bacteria that don't produce oxygen. These bacteria use hydrogen sulfide instead of water for photosynthesis. They thrive in this environment. The ocean surface might be covered in oily films of organic compounds. The water smells of sulfur, rotten eggs. The ocean floor is black mud, rich in organic material from dead bacteria. But no animals, no fish, no corals, no shells, nothing that needs oxygen. The tidal zones are harsh. Water evaporates quickly in the heat. Salt crusts form. Nothing complex survives here. It's a world that would be completely alien to us, hostile, unrecognizable. And yet, it's Earth, the same planet we live on, just a billion years later. This vision is sobering. It forces us to confront the temporary nature of the conditions we enjoy. Earth hasn't always been habitable for us, and it won't always be. We exist in a narrow window, a special time when conditions are just right. Oxygen in the air, moderate temperatures, liquid water, stable climate. This is not the norm in Earth's history. It's an interlude, a brief period of grace. Before and after this window, Earth is a different world, inhospitable to complex life. We're living in the sweet spot, the Goldilocks moment. And appreciating this changes your perspective. It makes you realize how extraordinary our current situation is, how lucky we are to exist now in this time on this oxygen-rich planet. This knowledge doesn't diminish life. It enhances it. It adds depth and meaning to every breath. Let's dig deeper into why this matters right now, even though it's a billion years away. You might think, why should I care about something that's going to happen so far in the future? Humanity might not even exist in 1,000 years, let alone a billion. And you'd be right to ask that question. But understanding Earth's oxygen deadline isn't really about worrying about something distant. It's about understanding the systems that keep us alive right now. The oxygen in the air didn't just appear, it's maintained by a delicate balance of processes. Photosynthesis produces it, respiration and decay consume it. Geological processes both produce and consume it. These systems are in balance now, but that balance isn't guaranteed forever. And understanding how it will eventually fail helps us understand how it works now, how fragile it might be, how things we do today could potentially disrupt it. The current climate crisis is fundamentally different from the oxygen crisis that's coming. Climate change is happening because we're adding carbon dioxide to the atmosphere, burning fossil fuels, releasing carbon that was stored underground for millions of years. This increases the greenhouse effect, traps more heat, warms the planet, melts ice, raises sea levels, changes weather patterns. These are serious problems with serious consequences, but they're not going to make oxygen disappear. In fact, higher carbon dioxide levels might actually help plants grow in some contexts, producing more oxygen. The oxygen crisis isn't about too much carbon dioxide, it's about too little. When carbon dioxide drops below the levels plants need to photosynthesize, oxygen production stops. That's the critical difference. Climate change is a problem we created and can potentially solve. The oxygen decline is a natural consequence of the aging sun and the carbon cycle. We didn't cause it and we can't stop it. But studying the oxygen decline teaches us important lessons. It shows us that planets aren't static. They evolve. Conditions that seem permanent are actually temporary. Earth has been through many different states in its history. It started as a molten ball, then cooled and formed a solid crust, then developed oceans, then developed an atmosphere. That atmosphere changed composition multiple times, from reducing to oxidizing, from carbon dioxide rich to oxygen rich, and now, in the future, it will change again, back to an oxygen poor state. Each of these changes happened for understandable physical and chemical reasons, not random, not mysterious, caused by processes we can model and understand. This gives us a framework for thinking about planetary evolution, for understanding not just Earth but other planets, for thinking about where we might find life elsewhere in the universe and what conditions it would need. The oxygen timeline also gives us perspective on the Anthropocene, the current epoch defined by human impact on Earth. We worry about the damage we're doing: pollution, deforestation, species extinction, ocean acidification. These are legitimate concerns. But in the grand sweep of Earth's history, human civilization is a blip. All of recorded human history, about 5,000 years, is 0.0005% of Earth's existence. Modern industrial civilization, about 200 years, is incomprehensibly tiny in geological terms. And even if we continue for thousands or tens of thousands of years, we're still just a moment. The Earth before us was wild and will be wild after us. This doesn't mean our actions don't matter. They matter enormously to us, to the species we share the planet with right now, to our children and their children. But they don't change Earth's ultimate trajectory. The sun will keep brightening. Carbon dioxide will eventually decline regardless of what we do. Oxygen will disappear on its schedule. We can damage Earth in the short term, but we can't change its long-term fate. That's both humbling and, in a strange way, freeing. We're not as powerful as we sometimes think. We're passengers on this planet, not drivers. Let's talk more about the carbon dioxide cycle because it's central to understanding the oxygen crisis. Carbon is constantly moving between different reservoirs on Earth. The atmosphere, the oceans, the land, living organisms, rocks. Each reservoir contains carbon in different forms. The atmosphere has carbon dioxide gas. The oceans have dissolved carbon dioxide and carbonate ions. Plants have carbon in their tissues as carbohydrates, proteins, fats. Animals have carbon in their bodies. Rocks have carbon as carbonates like limestone or as organic matter in shales and coal. Carbon moves between these reservoirs through various processes. Photosynthesis moves carbon from air to plants. Respiration moves it back. Death and decay move it to soil. Erosion moves it to oceans. Marine organisms build shells from carbonate. When they die, shells sink and form limestone. Subduction at tectonic plate boundaries drags carbonate rocks into Earth's mantle. Heat and pressure release carbon dioxide. Volcanoes bring it back to the surface. The whole system is a giant cycle operating on timescales from seconds to hundreds of millions of years. The key insight is that weathering acts as a thermostat. When Earth is warm, weathering speeds up. More rain, more chemical reactions, more carbon dioxide pulled from the air and deposited as carbonate rocks. This reduces the greenhouse effect. Earth cools. When Earth is cool, weathering slows down. Less carbon dioxide pulled from the air. Volcanic emissions of carbon dioxide accumulate. Greenhouse effect strengthens. Earth warms. This negative feedback has kept Earth's temperature relatively stable for billions of years, despite the sun getting steadily brighter. Early Earth with a dim sun was kept warm by high carbon dioxide levels. Modern Earth with a brighter sun stays temperate with lower carbon dioxide. The weathering thermostat adjusts. This is why Earth hasn't frozen solid or boiled away. The carbon cycle stabilizes climate. But there's a limit. The weathering thermostat can only work if there's enough carbon dioxide to start with. And as the sun continues brightening, weathering will eventually pull carbon dioxide levels so low that the thermostat fails. Plants can't extract enough carbon dioxide from the air to photosynthesize. They die. Weathering slows because dead plants mean less organic acids in soil, which means less aggressive weathering. But by then it's too late. The decline has started. Oxygen production stops. The balance tips. And there's no recovery. This is the critical threshold, the point of no return. Once carbon dioxide drops below the minimum photosynthetic threshold and plants die off, the system can't restore itself. It's a one-way transition, and the models predict this happens in about 1 billion years. Now let's talk about what this means for complex life. When we say complex life, we mean multicellular organisms, animals, plants, fungi, things you can see with your eyes, things with tissues and organs and specialized cells. Complex life requires certain conditions: energy, water, moderate temperatures, and, for most complex life on Earth, oxygen. The only complex organisms that don't need oxygen are a few weird specialists living in oxygen-free environments. But they're rare. The vast majority of animals, plants, and fungi need oxygen. They've evolved in an oxygen-rich world. Their biochemistry depends on it. Their cells use oxygen to generate energy through aerobic respiration. This process is far more efficient than anaerobic metabolism. You get about 20 times more energy from a molecule of glucose using oxygen than without it. This energy abundance allowed evolution of large bodies, fast metabolism, active lifestyles, intelligence, all of the things we associate with complex life. Without oxygen, you can't have large complex organisms. The energy demands are too high. Anaerobic metabolism can't meet them. This is why before the Great Oxidation Event, life was all single-celled. Bacteria and archaea. Nothing bigger. They didn't need much energy. They lived slowly, reproduced slowly, evolved slowly. After oxygen appeared, everything changed. Eukaryotic cells evolved. These are cells with nuclei and mitochondria. Mitochondria are the power plants of the cell. They use oxygen to generate energy. With mitochondria, cells could generate enough energy to be active, to move, to sense, to respond, to coordinate. This enabled multicellular life. First simple things like sponges, then more complex animals, then plants colonizing land, then insects and vertebrates, then mammals and birds, an explosion of complexity and diversity, all enabled by oxygen. When oxygen goes away, this complexity goes with it. Earth reverts to a microbial world, bacteria and archaea only. Simple, small, slow, that's the future, a return to the past. Some might wonder if evolution could produce new forms of complex life that don't need oxygen. Could animals evolve to use some other metabolism? The answer is almost certainly no. Not in the time frame available. Evolution works with what exists. It modifies existing structures and biochemistries. It doesn't reinvent from scratch. All complex life on Earth uses aerobic respiration. It's deeply embedded in our cells, our mitochondria, our DNA. Switching to a completely different energy generation system would require rebuilding cells from the ground up. That's not something evolution can do. And even if it could, there's no evolutionary pressure to do so until oxygen disappears. And once oxygen disappears, complex organisms die. They don't survive to evolve alternatives. Maybe if oxygen declined very slowly over tens or hundreds of millions of years, there would be time for adaptation. But the models show a rapid collapse. 10,000 years. That's nowhere near enough time for evolution to develop entirely new metabolisms. Complex life won't adapt. It will simply end. This raises philosophical questions about the nature of life and intelligence. If complex life on Earth is temporary, limited to a specific window when conditions are right, what does that say about life in the universe? How common is oxygen? How long do oxygen-rich atmospheres last on other planets? Are we typical or unusual? These questions matter for the search for extraterrestrial life. If oxygen-rich atmospheres are rare and short-lived, complex alien life might be rare too. Most planets might go through a bacterial phase and that's it. brief windows of complexity separated by vast stretches of simple life. Or maybe Earth is unusual. Maybe other planets maintain oxygen longer. Maybe some never get oxygen at all, but evolve complexity through other means. We don't know. We've only studied one planet in detail. But Earth's oxygen timeline gives us clues. It tells us oxygen is a product of life. It requires photosynthesis. It requires specific planetary conditions. It's not a given. It's a delicate, temporary state. And if that's true here, it might be true elsewhere. The universe might be full of planets that had brief periods of oxygen surrounded by much longer periods without it. If so, finding complex alien life becomes much harder. You have to catch a planet during its oxygen window, and those windows might be rare in both space and time. Let's return to Earth and walk through the stages of oxygen decline in even more detail because the specifics matter. We're at stage 0 right now, oxygen stable at 21%. Plants thriving, animals thriving, oceans full of life, land covered in vegetation, ice at the poles, climate stable enough for civilization. This stage lasts roughly another 500 million years. During this time, slow changes happen. Continents drift, species evolve and go extinct. The sun gets slightly brighter each million years. Average temperatures rise a bit. But nothing catastrophic. Earth remains recognizably Earth. Habitable, beautiful. This is the long goodbye. The last period of stability before things start to change noticeably. Stage 1 begins around 500 million years from now. Carbon dioxide levels have been declining for millennia. They're now low enough that C3 plants, which include most trees and many crops, start struggling. They need higher carbon dioxide levels to efficiently photosynthesize. C4 plants, which are more efficient at extracting carbon dioxide, become dominant. Grasslands expand, forests shrink, but vegetation still covers much of the land. Oxygen is still around 18 to 20%, plenty for animals. But the biosphere is under stress, higher temperatures, lower carbon dioxide. Some species go extinct, others adapt. This is a transition period. Earth is changing, but still habitable. Stage 1 lasts maybe 200 million years. A long, slow shift from the world we know to something hotter and drier, but still alive. Stage 2 starts around 700 million years from now. Carbon dioxide is now very low. Even C4 plants struggle. Photosynthesis is barely functional. Plant life is patchy, restricted to areas with higher moisture and cooler temperatures, maybe near coasts, maybe at high latitudes. Most of the land is barren. Deserts dominate. Oxygen levels are dropping noticeably now, maybe down to 12 or 15%. This is enough for some animals, but not all. Large active animals with high oxygen demands are gone. Only small, slow-moving creatures persist. The oceans are warming. Oxygen levels in seawater are dropping. Many marine species go extinct. Only tolerant species remain. Stage 2 is the collapse. The biosphere is failing. It lasts maybe 100 million years. A rapid transition by geological standards from a living world to a dying one. Stage 3 is the final act. Around 900 million years from now, carbon dioxide is almost gone. The last plants die. Oxygen production stops. And over the next 10,000 years, oxygen disappears from the atmosphere. It reacts with volcanic gases, with rocks, with methane from bacteria. Within a geological instant, the breathable atmosphere is gone. Any animals that survived stage 2 suffocate. The oceans become anoxic. hydrogen sulfide builds up. The surface becomes a toxic chemical soup. Only bacteria survive, anaerobic species that thrive without oxygen. They take over. The planet turns purple and green with bacterial mats. The sky is hazy with methane. Stage 3 is the new normal. And it lasts until the sun's expansion destroys the planet about 1 billion years later. Earth spends its final billion years as a bacterial world. Alien, hostile, dead to everything we recognize as life. Understanding these stages helps us grasp the magnitude of the transformation. Earth doesn't just get a little warmer or a little drier, it completely changes. From oxygen-rich to oxygen-free, from complex to simple, from diverse to monotonous, from beautiful to bleak. It's not a gradual fading, it's a collapse, and once it happens, there's no going back, no recovery, no second chance. This is the final state, the ultimate fate of our living planet. And while it's 1 billion years away, knowing it's coming changes how you see the world around you. Every forest, every ocean, every breath of air. It's all temporary, precious, irreplaceable. This isn't the norm. It's a gift. And someday, far in the future, that gift will be taken back. Earth will continue, but life as we know it will not. There's something profound about imagining Earth without oxygen that forces us to reconsider what we mean by a living planet. Right now, if you look at Earth from space, the signs of life are obvious. Green continents from vegetation, blue oceans full of phytoplankton, white clouds from water evaporated by biological and physical processes. The atmosphere itself is a biosignature. 21% oxygen is unstable. It reacts with everything. It should disappear quickly. The fact that it's maintained at high levels is direct evidence of life. Specifically, photosynthetic life constantly replenishing it. When scientists look for life on planets around other stars, one of the key things they search for is oxygen in the atmosphere. Find oxygen and you've likely found photosynthetic life. But Earth's future reminds us this signature is temporary. A planet can have oxygen for a while, then lose it. The oxygen signature doesn't mean life will persist forever, just that it exists now. This has implications for how we interpret observations of exoplanets. If we detect oxygen in an exoplanet's atmosphere, we might get excited. Life. But maybe we're just catching that planet during its oxygen phase. If we observe it again in 1 billion years, the oxygen might be gone. This doesn't mean the planet died. It might still have bacterial life, but complex life would be gone. This suggests that when we search for life, we should think about planetary age. Young planets might not have developed oxygen yet. Old planets might have lost it. There's a sweet spot, a temporal window, and we need to catch planets during that window to detect oxygen signatures. This makes the search harder. It's not enough for a planet to be in the habitable zone with the right size and the right star. It also needs to be the right age. In its oxygen-producing phase, that narrows the targets considerably. Another thought that emerges from contemplating Earth's oxygen deadline is about the nature of home. Earth is our home, the only home humanity has ever known. We evolved here. Our bodies are adapted to this environment, this atmosphere, this gravity, this temperature range. We're Earth creatures through and through. But Earth won't always be home. Eventually, it will become inhospitable, not in 1 billion years when oxygen disappears. Earlier. In about 500 million years, maybe less, Rising temperatures will make Earth increasingly difficult for complex life. By the time carbon dioxide levels start dropping critically, Earth will already be largely uninhabitable by us. We'll need to have moved elsewhere, to other planets, other star systems, or we'll be gone, extinct. This reality hangs over discussions of space exploration. It's not just about curiosity or adventure, it's about survival. Long-term survival requires leaving Earth, because Earth has an expiration date. We can't stay forever, but here's the paradox. No matter where we go, those places will also be temporary. Mars will eventually become uninhabitable as its atmosphere continues thinning. Venus is already uninhabitable. The gas giants aren't options. We'd have to go to moons like Europa or Enceladus, living under ice in underground oceans. Or we'd have to leave the solar system entirely, find planets around other stars. But those stars also age. Those planets also change. Everywhere we go will eventually become uninhabitable. Maybe in millions of years, maybe billions. But eventually, there's no permanent home in the universe, just temporary shelters. This isn't depressing if you think about it right. It means home isn't a place, it's what we create, the communities we build, the connections we form, the meaning we make. Those can move with us, from planet to planet, from star to star. If humanity survives long enough, we'll be a nomadic species, moving as old homes die and new ones become available, carrying our culture and knowledge and identity with us. That's actually beautiful in a way, not tied to one rock, but adaptable, resilient, capable of thriving anywhere we choose to go. The oxygen deadline also makes you think differently about preservation and conservation. Why protect ecosystems if Earth is doomed anyway? If forests will die in 1 billion years, why save them today? The answer is because they matter now. The billion-year timeline doesn't make current extinctions less tragic, doesn't make habitat destruction less harmful. We're not saving Earth for 1 billion years from now. We're saving it for today, for this century, for the next 1,000 years, for as long as humanity and complex life persist. That's still an enormous span of time. Millions of generations, countless experiences, infinite value. The oxygen deadline shows us that nothing lasts forever. But that doesn't mean things don't matter while they exist. If anything, their temporariness makes them more precious, more worth protecting. A beautiful moment isn't less beautiful because it ends. It's more beautiful because it's fleeting. Earth's biosphere is a beautiful moment. It's been going for several 100 million years. It might continue for several 100 million more. That's a long moment by our standards. Worth preserving, worth celebrating, worth fighting for. Let's also talk about what comes after the oxygen is gone, because that future is part of Earth's story too. For 1 billion years after oxygen disappears, Earth will host only anaerobic life. Bacteria and archaea that don't use oxygen. Some use sulfur compounds. Some use iron. Some ferment organic material. Some use methane. There are many anaerobic metabolisms. These organisms will flourish in the oxygen-free world. They'll form mats and biofilms in the oceans. They'll live in soil and rocks. They'll adapt to the high temperatures and harsh conditions. And they'll be successful. From their perspective, this is a return to paradise. Earth was their world for 2 billion years before oxygen showed up. Oxygen was a catastrophe for them. They retreated to oxygen-free refuges. Now they're back. The planet is theirs again. They'll diversify, evolve, explore new niches. For them, Earth's oxygen-free future is an opportunity. But even bacteria can't last forever. As the sun continues brightening, Earth keeps heating. The oceans evaporate into the atmosphere. Water vapor is a powerful greenhouse gas. It traps heat. This creates a runaway greenhouse effect. More heat means more evaporation, which means more heat. Eventually, Earth's temperature rises above the boiling point of water. The oceans boil away. Water vapor fills the atmosphere. Solar ultraviolet light breaks water molecules apart into hydrogen and oxygen. Hydrogen escapes to space. Oxygen reacts with rocks. The planet becomes dry, scorched. Eventually, Earth looks like Venus, a hellish world with a thick carbon dioxide atmosphere and surface temperatures hot enough to melt lead. No liquid water anywhere, no life, not even bacteria. Earth will spend its final few 100 million years as a dead planet, sterile, lifeless, waiting for the sun to expand and destroy it completely. This is the ultimate fate, not just no oxygen, no life at all, total death. This trajectory from living world to dead world is what planetary scientists call the habitable zone's inner edge. Every star has a habitable zone. The region where a planet can have liquid water on its surface. Too close to the star and it's too hot. Water evaporates. Runaway greenhouse. Too far and it's too cold. Water freezes. Snowball planet. Earth is currently comfortably in the sun's habitable zone. But as the sun brightens, the habitable zone moves outward. Eventually, Earth will be inside the inner edge. Too close to the now brighter sun, the runaway greenhouse becomes inevitable. Mars, currently outside the outer edge and frozen, will move into the habitable zone. For a while, maybe a few 100 million years, Mars might be warm enough for liquid water. It might become the solar system's habitable planet while Earth bakes. Then the sun brightens more, and Mars becomes too hot too. Eventually, the habitable zone moves beyond Mars, maybe reaching the asteroid belt. Europa and Enceladus might thaw, but by then, the sun is approaching the end of its main sequence lifetime. It starts expanding, becomes a red giant, swallows Mercury, swallows Venus, possibly swallows Earth. The habitable zone briefly moves to the outer solar system. Titan might become warm, but it doesn't last. The sun becomes unstable, sheds its outer layers, becomes a white dwarf. The solar system is left cold and dark. No habitable zone, no possibility of life. The sun's life and the solar system's habitability are finite. They end, and everything that depended on them ends too. Contemplating these timescales and transformations is dizzying. The mind struggles to grasp billions of years, to imagine Earth changing so profoundly, to accept that everything familiar will vanish. But there's value in the attempt. It gives perspective. It shows us our place in time. We exist in a narrow window. We're alive during Earth's oxygen phase, during the time when conditions allow complex life. Before the oxygen existed, only simple life was possible. After it disappears, only simple life will be possible again. We exist during the exception, the special time. This makes our existence remarkable, not in the sense that we're important to the universe. We're not. The universe doesn't care about us. But in the sense that we're rare, lucky. We get to experience a state of the planet that's temporary, that hasn't always existed and won't always exist. We're the beneficiaries of a cosmic coincidence. The right planet, the right star, the right time. If we'd evolved 1 billion years earlier, we couldn't have. Oxygen wasn't available yet. If we'd evolved 1 billion years later, we couldn't have. Oxygen will be gone. We exist in the narrow window, and that's extraordinary. This perspective can be liberating. So many of our anxieties are about the future. What will happen to me, to my family, to humanity? What will the world look like in 100 years, 1,000? We worry about legacy, about meaning, about whether what we do matters. The oxygen deadline reminds us that in the very long term, nothing we do matters to the universe. Earth will lose its oxygen whether we cure cancer or not, whether we achieve world peace or destroy ourselves in war, whether we spread to the stars or go extinct tomorrow. The universe's trajectory is set by physics, not by our choices. But this doesn't make our choices meaningless. It just changes the frame. Our choices matter to us, to our experience, to the people we affect, to the generations that come after us. That's enough. We don't need cosmic significance. We just need local significance, meaning in the here and now, impact on the people and places we touch. That's real, that's valuable, and the fact that it's temporary doesn't diminish it. If anything, it enhances it, because temporary things are precious precisely because they won't last. The oxygen deadline is a reminder that Earth is a dynamic system. Nothing about it is guaranteed. The air we breathe, the water we drink, the moderate climate, the diverse ecosystems. All of these exist because of complex interactions between the sun, the planet, the atmosphere, the oceans, and life. These interactions maintain conditions suitable for complex life, but they're not permanent. They're contingent, dependent on circumstances that will change. And when they change enough, the conditions we depend on will disappear. This is true not just on geological timescales, but on human timescales too. Climate change is a disruption of these systems, not as dramatic as the oxygen loss that's coming, not as final, but still serious, still capable of making Earth less hospitable, less stable, less predictable. Understanding Earth's long-term fate helps us appreciate how delicate the systems are that keep us alive, how careful we need to be, how much we depend on processes we barely understand and can't control. This isn't about fear, it's about respect. Respect for the planet, for its complexity, for its power, for its limits. In the end, the story of Earth's oxygen is a story about life itself. Life emerged on Earth about 4 billion years ago. For half of Earth's history, life was simple. Bacteria and archaea only. Then photosynthesis evolved. Oxygen accumulated. The planet changed. Complex life became possible. For the next 2 billion years, life diversified, explored every niche, colonized every environment, became more complex, more beautiful, more strange. And now, looking forward, we see the reversal. Oxygen will disappear, complex life will end, Earth will return to its simple microbial state. Then even that will end as the planet heats beyond habitability. Life on Earth is a temporary phenomenon, a brief flourishing between the planet's sterile beginning and sterile end. We're living during the flourishing, the peak, the golden age, and knowing this makes every moment more precious. Every sunrise, every forest, every creature, they're all part of this temporary masterpiece, this living planet, this oxygen world. It won't last forever, but it exists now, and that's enough. That's everything. There's one more aspect worth exploring before we move forward, and that's the comparison to other planetary catastrophes in Earth's history. The oxygen deadline isn't the first time Earth has faced a fundamental transformation. The Great Oxidation Event itself was catastrophic for the life that existed before it. For 2 billion years, Earth was an anaerobic world. Life thrived without oxygen. Then cyanobacteria evolved oxygenic photosynthesis, and everything changed. Oxygen accumulated in the atmosphere. For anaerobic organisms, this was poison. Imagine if the air suddenly filled with a corrosive, toxic gas. That's what happened to them. Most died. Some survived in oxygen-free refuges, deep mud, hot springs, animal guts. But their world was gone. Destroyed by what we now consider a gift, the rise of oxygen. This reminds us that catastrophe is perspective dependent. What is disaster for one form of life is opportunity for another. The oxygen crisis that's coming will be disaster for us, for complex life, but for anaerobic bacteria, it's liberation, the return of their world. Earth has also been through multiple mass extinctions. The end Permian extinction 250 million years ago killed 90% of marine species and 70% of land species. The end Cretaceous extinction 66 million years ago killed the dinosaurs and most large animals. But life recovered from these events. New species evolved, ecosystems rebuilt, diversity returned. Within a few million years, you couldn't tell a mass extinction had happened except by looking at the fossil record. These extinctions were severe but temporary. Life persisted because the fundamental conditions for life remained. Oxygen in the atmosphere, liquid water, moderate temperatures. The oxygen crisis is different. It's not a temporary disruption. It's a permanent change, a one-way transition. When oxygen disappears, it doesn't come back. The conditions that allowed its accumulation, specifically life actively producing it, will be gone. Without photosynthesis, there's no oxygen source. The atmosphere returns to its pre-oxygenated state and stays there. This makes the oxygen crisis unique in Earth's history. Not just another mass extinction, but the end of an era, the end of complex life's possibility. Another comparison worth making is to human-caused threats: nuclear war, pandemic, climate change, artificial intelligence gone wrong. These are all potential catastrophes that could harm or even end human civilization. They're worth worrying about and working to prevent. But they're different in nature from the oxygen crisis. Human-caused threats are preventable. We can choose not to have nuclear war. We can develop pandemic preparedness. We can reduce emissions and slow climate change. We can regulate AI development. These outcomes depend on our choices. The oxygen crisis doesn't. It's baked into Earth's future. It follows from physics and chemistry and the sun's evolution. No choice we make changes it. This distinction matters. For human-caused threats, there's urgency. We need to act now, change our behavior, develop solutions. For the oxygen crisis, there's no urgency. It's 1 billion years away. We can't prevent it and don't need to try. What we can do is learn from it, understand planetary systems, appreciate our current situation, plan for long-term survival as a species if we last that long. But we don't need to panic about the oxygen deadline. We need to appreciate it, use it to contextualize other concerns, recognize what's truly temporary versus what's truly permanent. The research that predicted Earth's oxygen loss wasn't done in isolation. It's part of a broader effort to understand planetary habitability. How long do planets remain habitable? What factors affect habitability? How can we predict which planets might host life? These questions drive a lot of modern planetary science and astrobiology. By studying Earth's past and future, we build models that apply to planets around other stars. We learn that habitability is temporary, that atmospheres evolve, that what seems stable is actually changing. This knowledge is crucial as we search for life elsewhere. We're not just looking for planets in habitable zones. We're looking for planets at the right stage of their evolution, young enough to have developed life, but not so old that they've lost the conditions life needs. Earth gives us a template, a case study, a warning about what to expect, and this informs our search, makes it more sophisticated, more realistic, more likely to succeed in finding life if it's out there. One final thought before we continue. The oxygen deadline story is ultimately about time, geological time, deep time, time spans so long they dwarf human comprehension. 1 billion years is incomprehensible. You can say the number, but you can't really grasp it. The best we can do is use comparisons and ratios. 1 billion years is to 1 year as 1 year is to 32 seconds. If you compressed Earth's history into a single day, complex life would appear around 3 p.m. Humans would show up a few seconds before midnight, and the oxygen crisis would happen about 3 a.m. tomorrow. These comparisons help, but they still don't convey the reality. 1 billion years is deep time, true deep time, and learning to think in deep time changes you. It gives perspective on the present, makes your lifespan feel short, makes human history feel recent, makes current problems feel temporary. This isn't nihilistic, it's freeing. Your problems matter to you, but they're not eternal. They're moments in time. They'll pass. Everything passes. Even oxygen, even Earth, even the sun. Time consumes everything. Understanding this, really understanding it, changes your relationship with existence, makes you more present, more grateful, more aware, because if everything is temporary, then the only moment that truly exists is now, this moment, this breath, and that's where meaning lives, not in the distant future, not in the deep past, but here, now, breathing oxygen, living on a planet that makes it possible for this brief, extraordinary window in cosmic time. Looking at other planets in our solar system teaches us valuable lessons about what can happen when atmospheres change. Mars and Venus are particularly instructive because they show us different failure modes, different ways a planet can become uninhabitable. Mars lost most of its atmosphere early in its history. It's a thin, cold desert now. The atmosphere is mostly carbon dioxide, but so thin it's almost a vacuum. About 1% the pressure of Earth's atmosphere. You can't breathe it, not just because it's carbon dioxide, but because there's not enough of it. Your blood would boil in the low pressure. Mars wasn't always this way. Early Mars had a thicker atmosphere, liquid water on the surface, rivers, lakes, maybe even an ocean. We can see the evidence in the geology, ancient river valleys, lake beds, shorelines. Something happened, and Mars lost its atmosphere. The leading theory is that Mars lost its magnetic field. Earth has a magnetic field generated by its liquid iron core. This field deflects the solar wind, the stream of charged particles flowing from the sun. Without a magnetic field, the solar wind strips away atmosphere. Mars is smaller than Earth. It cooled faster, its core solidified, the magnetic field shut off. Then, over hundreds of millions of years, the solar wind stripped away most of the atmosphere. What's left is the thin remnant we see today, Mars is a cautionary tale. Lose your magnetic field and you lose your atmosphere. Lose your atmosphere and you lose your water. Lose your water and you become a frozen desert. Dead. Venus went the other way. Too much atmosphere. Venus is almost the same size as Earth. Similar mass, similar composition. It should be Earth's twin. But it's hell. The surface temperature is 470 degrees Celsius, hot enough to melt lead. The atmospheric pressure is 90 times Earth's, like being a kilometer underwater. The atmosphere is almost entirely carbon dioxide with clouds of sulfuric acid. Nothing can survive there. Not even our toughest spacecraft last more than a few hours. Venus wasn't always like this. Early Venus might have been habitable. It might have had oceans. But Venus is closer to the Sun than Earth. It received more solar energy. Water evaporated into the atmosphere. Water vapor is a greenhouse gas. It trapped heat. This caused more evaporation, more greenhouse effect, more heat, a runaway feedback loop. Eventually, the ocean boiled away completely. Water vapor filled the atmosphere. Solar ultraviolet broke water molecules apart. Hydrogen escaped to space. Oxygen reacted with rocks. Venus lost its water and became a hothouse. The thick carbon dioxide atmosphere maintains the extreme temperature. Venus shows us what happens when a planet gets too hot. When the greenhouse effect runs away, it becomes permanently uninhabitable. Earth is between these extremes, not too thin like Mars, not too thick like Venus, just right. But this Goldilocks state is temporary. Earth is slowly drifting toward the Venus scenario. As the sun brightens, Earth will heat up. Eventually, the oceans will start evaporating. Water vapor will build up in the atmosphere. The greenhouse effect will strengthen. We'll enter a runaway phase. The oceans will boil away. Earth will become Venus. This is the ultimate fate regardless of the oxygen timeline. Even if oxygen somehow persisted, Earth would still become uninhabitable due to rising temperature. The oxygen loss just happens first. It's the opening act, the preview. The real finale is the Venus transition. Both fates are sealed by the aging sun. Both are inevitable. Mars, Earth, and Venus show us the range of possibilities. Lose your atmosphere, and you freeze. Keep it, but get too hot and you bake. There's a narrow window of habitability, and that window moves as stars age. This brings us to the search for life on planets around other stars. We've discovered thousands of exoplanets, planets orbiting stars other than the Sun. Some are in their star's habitable zone, the region where liquid water could exist on the surface. These planets are candidates for hosting life. But finding them is just the first step. We need to characterize them, measure their size, their mass, their density, and, most importantly, analyze their atmospheres. This is incredibly difficult. Planets are tiny and dim compared to their stars. Separating the planet's light from the star's light is like trying to see a firefly next to a searchlight. But we're developing techniques. Transit spectroscopy is one method. When a planet passes in front of its star, the starlight passes through the planet's atmosphere. Different gases absorb different wavelengths. By analyzing the spectrum of the starlight, we can detect what gases are in the atmosphere. This has allowed us to detect water vapor, methane, and other compounds in exoplanet atmospheres. Oxygen is a key target. If we detect oxygen in an exoplanet's atmosphere, it's strong evidence of life. Oxygen is reactive. It shouldn't persist without something constantly producing it. On Earth, that something is photosynthesis. If we find oxygen elsewhere, photosynthesis is the most likely explanation. This would be the first detection of extraterrestrial life. Enormous, revolutionary. But Earth's oxygen timeline complicates this search. Oxygen is a temporary biosignature. A planet needs to be in its oxygen-producing phase for us to detect it. Too young and photosynthesis hasn't evolved yet. Too old and oxygen has disappeared. We need to catch planets at the right age. This narrows our target list. We should focus on planets around stars similar to the Sun, but slightly younger. Stars that have had time to develop complex planetary systems and possibly life, but haven't aged enough to make their planets uninhabitable. This is a sweet spot in both space and time. The oxygen timeline also tells us that even if we find oxygen, we're seeing a temporary state. That exoplanet might have oxygen now, but it won't forever. Just like Earth. This doesn't diminish the discovery, it just contextualizes it. Life on that planet, if it exists, is also living on borrowed time, just like us. Everything is temporary. Every biosphere has an expiration date. This is a universal truth, not just Earth, everywhere, and understanding this helps us appreciate what we're looking for. We're not searching for eternal paradises, we're searching for temporary havens, places where life has emerged and flourished for a while, places having their moment, just like Earth is having its moment. Finding another planet in its moment would be profound. It would tell us we're not alone, not unique, that life is a pattern the universe repeats, that wherever conditions are right, life emerges, flourishes, then fades as conditions change. It's the cycle, the pattern, and we're part of it. So, when oxygen disappears from Earth, will anything survive? The answer is yes. Lots of things, just not the things we're familiar with. Bacteria and archaea that don't need oxygen will thrive. These are organisms that have been around since the beginning. They've survived every mass extinction, every climate change, every catastrophe Earth has experienced. They're the ultimate survivors, and they'll inherit the oxygen-free Earth. Some will use sulfur compounds for metabolism. Sulfate-reducing bacteria take sulfate and turn it into hydrogen sulfide. They live in oxygen-free environments today. Ocean sediments, deep underground, hot springs. When oxygen disappears, they'll expand, fill every niche. The oceans will turn purple and green with sulfur bacteria. The smell will be overwhelming. Hydrogen sulfide everywhere. But for these bacteria, it's perfect. This is their preferred environment. Other bacteria will use fermentation, breaking down organic compounds without oxygen, producing methane and other gases as waste. Methanogens, methane-producing archaea, will flourish. They'll pump methane into the atmosphere. Methane levels will rise dramatically. The atmosphere will become hazy. Photochemical reactions in the upper atmosphere will create complex organic compounds, similar to what happens on Titan. The sky will be murky, visibility poor, but life will be everywhere, microscopic, simple, but abundant, diverse. These organisms will form complex communities, mats and biofilms, different species cooperating or competing, exchanging nutrients and waste products, creating micro-environments within the larger harsh environment. Life finds a way, even without oxygen, even in conditions that would kill us instantly. Bacteria adapt, survive, thrive. There might also be extremophiles we haven't discovered yet. organisms with metabolisms we can't imagine. Earth's biosphere today is limited by oxygen. Oxygen enables certain biochemistries but prevents others. When oxygen disappears, new possibilities open up. Organisms that were suppressed by oxygen's presence might emerge, evolve, diversify. We might see entirely new forms of life, new metabolisms, new adaptations. Not complex, still single-celled, but novel, strange, unexpected. This is speculation, but it's based on what we know about evolution and ecology. Remove a dominant constraint and new niches open, new opportunities arise. The oxygen-free Earth will be different from the early oxygen-free Earth because it has billions of years of additional evolution. Different starting organisms, different environmental conditions. The details will vary, but the principle holds. Life persists, changes, continues. As long as liquid water exists and temperature stays within certain bounds, life finds ways to survive. But there's a hard limit. Eventually, Earth becomes too hot, even for extremophiles. When the oceans boil away and surface temperatures exceed 100 degrees Celsius everywhere, life ends. There are thermophiles, heat-loving bacteria that survive at high temperatures. Some live in boiling water. But there's a limit. Around 120 degrees Celsius, even the toughest known organisms die. Proteins denature, DNA breaks down, cells can't function. When Earth's surface exceeds this temperature, life is over. Not just complex life, all life. The planet becomes sterile. This happens in the late stages of the Venus transition. Probably a few 100 million years after the oxygen disappears, Earth will be lifeless for its final few 100 million years, a dead rock orbiting a dying star, waiting for the end. No bacteria, no archaea, nothing. Just heat and rock and a thick, poisonous atmosphere. The story of life on Earth will be complete. Beginning, middle, end. A finite story with a definite conclusion. Could we stop the oxygen decline? Could we intervene? Engineer a solution? Keep Earth habitable longer? These questions come up whenever people learn about the oxygen deadline. The answer is complicated. Technologically, maybe. In principle, you could imagine solutions. Artificially replenish carbon dioxide in the atmosphere. Build giant machines that release carbon dioxide from rocks or manufacture it from other compounds. This would provide the raw material for photosynthesis. Keep plants alive. Keep oxygen production going. Or you could forget about natural photosynthesis and build artificial systems. Solar-powered factories that split water and release oxygen. Space-based mirrors or shades to control how much sunlight reaches Earth. Keep temperatures from rising too much. Extend the habitable period. These are all theoretically possible. The physics and chemistry work. But the scale is absurd. We're talking about planetary engineering, controlling an entire planet's climate and atmosphere for millions of years. The energy requirements are enormous. The resources needed are beyond anything we can currently imagine, and you'd have to maintain it forever, or at least for as long as you want Earth to stay habitable. Any failure, any interruption, and the systems collapse, oxygen disappears, everything dies. There's also the question of why. Why go to such extreme effort to keep Earth habitable when you could just leave? Move to another planet, another star system, build habitats in space. Any of these options are easier than planetary scale engineering for millions of years. If humanity survives that long, we'll have the technology to live anywhere. We won't be dependent on Earth's biosphere. We'll create our own environments, our own atmospheres, our own ecosystems in artificial habitats or on terraformed worlds. Earth will be home in a sentimental sense, but not a practical one. We'll have moved on, spread out, diversified. So, spending enormous resources to keep Earth habitable seems pointless. Better to let Earth follow its natural trajectory, appreciate it while it lasts. Then move elsewhere when the time comes. This is assuming humanity survives that long, which is a big assumption. We might be gone long before the oxygen crisis, extinct from our own mistakes or just bad luck. In that case, the question is moot. Earth will lose its oxygen on schedule, and no one will be around to care. Even if we could and wanted to keep Earth habitable, there's something unsettling about it. Something that feels wrong. Earth is a natural system. It's evolved over billions of years. It has its own trajectory, its own fate. Interfering with that on a planetary scale feels hubristic, like we're trying to play God, control things beyond our understanding. There's wisdom in accepting limits, in recognizing that some things are beyond our control and should stay that way. Earth will run its course. Life will flourish and then fade. That's natural. That's okay. Our role isn't to prevent it. It's to appreciate it, to understand it, to be good stewards while we're here, but not to fight the inevitable, not to rage against the dying of the light, just to be present, aware, grateful, and, when the time comes, to move on. Let Earth rest. Let it return to the simple microbial state it came from. That's a kind of closure, a completion of the cycle, and there's beauty in that. What comes after the oxygen is gone. We've touched on this, but let's explore it more fully. Earth's final billion years will be divided into stages. First, the anaerobic bacterial world. This lasts as long as liquid water exists and temperatures stay below the thermal limit for life. Maybe 500 million years, maybe less. During this time, Earth is alive but simple. Bacteria everywhere, in the oceans, in rocks, in soil, forming thick mats and biofilms, metabolizing, reproducing, evolving. From space, Earth looks different but not dead. There's still a biosphere, still chemical processes driven by biology. The atmosphere is chemically out of equilibrium. Methane coexisting with carbon dioxide, hydrogen sulfide in significant amounts. These are biosignatures, evidence of life. If aliens observed Earth during this period, they might detect life through atmospheric analysis, even without oxygen. So, Earth remains a living world, just a different kind of living than we're used to. Then comes the sterile phase. As temperatures rise and water disappears, life ends. The last bacteria die. The planet becomes chemically simple. The atmosphere reaches equilibrium. Mostly carbon dioxide with nitrogen and trace gases. No more methane being produced. No more hydrogen sulfide. The chemistry becomes purely abiotic. Volcanic emissions, photochemical reactions in the atmosphere, weathering of rocks. But no biology. Earth is dead. From space, it looks like Venus. Thick atmosphere, high temperature, no signs of life. This phase lasts until the sun's expansion destroys Earth. Several 100 million years of sterile existence, a dead world orbiting a dying star. This is the final state, the end point, and there's no coming back, no recovery, no second chance. Earth's story ends here. But zoom out, and this isn't tragic, it's natural. Stars have lifetimes. Planets have lifetimes. The conditions that allow life are temporary. This is true everywhere in the universe. Every planet that hosts life will eventually lose it. Either the star dies, or the planet's orbit changes, or the atmosphere is lost, or some other catastrophe. Nothing lasts forever. Life is always temporary. Earth is not unique in this regard. It's typical, normal. And understanding this helps us see our place. We're living during Earth's living phase, the window when conditions allow complex life. This window will close, but it's open now. And that's what matters. Not the distant future, the present, this moment, this breath, this life, this planet, now. There's a bigger picture here about the nature of existence and meaning. If everything is temporary, if Earth will die, if the sun will die, if even the universe might eventually reach heat death, then where does meaning come from? How do we find purpose in a universe that seems ultimately futile? This is an old philosophical question, and there's no single answer. But one perspective that emerges from understanding Earth's oxygen timeline is that meaning is local, immediate. It doesn't come from cosmic significance or eternal legacy. It comes from the experience of being alive now, from the relationships we form, the beauty we appreciate, the knowledge we gain, the love we share. These things matter even though they're temporary. Maybe they matter more because they're temporary. A sunset is beautiful partly because it fades. A flower is precious partly because it wilts. Life has meaning partly because it ends. If everything lasted forever, nothing would feel special. It's the temporariness that creates value, the scarcity that creates appreciation. Earth's oxygen will disappear in 1 billion years. This doesn't make your life meaningless. It doesn't make your choices irrelevant. It doesn't diminish love or art or discovery or joy. Those things are real. They matter. They're meaningful. Not because they last forever, but because they exist at all. In a vast, mostly empty, mostly dead universe, the fact that Earth has oxygen and life and consciousness is extraordinary. That you get to experience it is a gift. That you get to be part of the living Earth, even for a brief time, is remarkable. The oxygen deadline reminds us of this. It puts everything in perspective, shows us how special and fragile and temporary our situation is. And this knowledge, far from being depressing, can be liberating. It can help us focus on what truly matters, not accumulating things, not achieving permanent legacy, but being present, being kind, being aware, appreciating the moment we're in, because this moment, this living planet, this breathable air, it's all temporary, it's all borrowed, and someday it will be returned. Our responsibility, then, isn't to prevent the oxygen decline. We can't. It's to make the most of the time we have, to be good stewards of the planet while complex life persists, to preserve ecosystems, protect species, reduce suffering, increase knowledge, create beauty. These aren't pointless endeavors just because Earth will eventually die. They're meaningful precisely because time is limited. We're the only species on Earth that knows Earth will lose its oxygen, that knows the planet has an expiration date. This knowledge comes with responsibility, not to prevent the inevitable, but to honor what we have while we have it, to treat Earth with respect, to treat life with reverence, to understand that we're part of something temporary and precious, and to act accordingly. This means taking care of the biosphere now, not for the sake of 1 billion years from now, for the sake of today, this century, the next 1,000 years, the timescale on which our actions actually matter. Climate change is a crisis not because it threatens Earth's long-term future, Earth will be fine in the long term. The planet has survived worse. Climate change is a crisis because it threatens human civilization and current ecosystems. It causes suffering, disrupts lives, drives species extinct. Those impacts are real and important, even though they're temporary in geological terms. Everything is temporary in geological terms. That doesn't make it okay to cause harm. If anything, it makes harm worse. Because time is limited, suffering is real, and we have the power to reduce it or increase it. That choice matters. That responsibility is real. Even knowing Earth will eventually become uninhabitable doesn't absolve us of the duty to care for it now. Why do scientists study Earth's oxygen future? What's the point of running computer models to predict something 1 billion years away? Several reasons. First, understanding Earth's long-term evolution helps us understand how planetary systems work. The same processes that will eventually deplete Earth's oxygen are operating today, just slowly. By modeling the extreme endpoint, we test our understanding of current systems. If the models can accurately predict Earth's future, it validates our understanding of the carbon cycle, atmospheric chemistry, and planetary evolution. This knowledge applies to other planets, other timescales. It helps us interpret observations of exoplanets and understand their potential for hosting life. Second, studying extreme scenarios helps us understand limits. What are the boundaries of habitability? How far can conditions change before life becomes impossible? Earth's oxygen timeline gives us one data point. It shows us that oxygen atmospheres are temporary, that complex life has a limited window, that planets evolve in ways that eventually preclude the life that emerged on them. This is useful information. It helps us calibrate our expectations, understand what's normal versus unusual, recognize patterns versus exceptions. The universe is vast. We need frameworks for understanding it. Earth's story is one framework, one example, one piece of the puzzle. Third, there's inherent value in knowledge, understanding the universe, how it works, where we fit into it. This has always driven human curiosity. We study the stars not because it helps us survive, but because we want to know. We study the past not because we can change it, but because we want to understand it. We study the future not because we can control it, but because we're curious. This is a fundamental part of being human, the drive to understand, to explore, to learn. Earth's oxygen deadline is part of this quest. It's a piece of knowledge about how planets work, how atmospheres evolve, how life fits into cosmic timescales. And that knowledge is valuable in itself, not for any practical application. Just for the sake of knowing, for the satisfaction of understanding, for the expansion of human knowledge. That's enough. That's always been enough. There's also something profound about looking that far into the future and seeing with scientific clarity what will happen. For most of human history, the future was mysterious, unknown, subject to the whims of gods or fate or chance. We had myths and prophecies, but no real knowledge. Now we can model the future, not perfectly, not in detail, but in broad strokes. We can see what's coming. We know the sun will brighten. We know temperatures will rise. We know carbon dioxide will decline. We know oxygen will disappear. These predictions are based on physics and chemistry, on mathematics and observation, on reason and evidence. They're not guesses, they're conclusions, derived from what we know about how the universe works. This is the power of science, to pierce the veil of the future, to see what's coming, to understand not just the past and present, but also what lies ahead. And while we can't change Earth's ultimate fate, we can at least understand it, know it, prepare for it in whatever ways make sense. That's progress. That's enlightenment. That's the human mind reaching across deep time to grasp the shape of things to come. In the end, Earth's oxygen deadline is a story about time, change, and the temporary nature of all things. Nothing lasts forever. Not oxygen, not Earth, not the sun, not even the universe as we know it. Everything has a beginning, a middle, and an end. Earth is in the middle of its story, the oxygen-rich phase, the time when complex life flourishes. This phase will end. But it hasn't ended yet. We're living in it now, breathing oxygen, walking on a green planet, looking up at a stable yellow star. This is extraordinary. This is rare. This is precious. Not because it lasts forever, because it doesn't, because it's temporary, because it's happening now and will eventually stop. That's what makes it meaningful. That's what makes it beautiful. That's what makes every breath worth taking and every moment worth savoring. Let's dive deeper into the specifics of how scientists model Earth's future, because the methodology is fascinating and reveals how far our understanding has come. The 2021 study by Ozaki and Reinhard wasn't just speculation. It was based on sophisticated computer simulations that integrated multiple complex systems. They started with solar physics models that predict how the sun's luminosity will increase over time. These models are well established. We understand stellar evolution. Stars burn hydrogen in their cores. As they do, the core contracts slightly and heats up. This increases fusion rates, which increases energy output. The sun gets brighter at about 10% per billion years. This isn't guesswork, it's physics. Then they layered in atmospheric chemistry, how gases in the atmosphere interact, how they absorb and emit radiation, how they trap heat, the greenhouse effect from carbon dioxide and water vapor, how these gases cycle between the atmosphere, oceans, and rocks. The model tracked carbon dioxide absorption by rainwater, chemical weathering of silicate rocks, the formation of carbonates, the subduction of those carbonates into Earth's mantle, volcanic outgassing returning carbon to the atmosphere. This is a complete carbon cycle model, operating over geological timescales, with all the known feedbacks and interactions. They also included biological processes, how photosynthetic organisms take up carbon dioxide, how they produce oxygen, how oxygen consumption through respiration and decay balances production, how changes in carbon dioxide levels affect photosynthesis rates. Below a certain threshold, photosynthesis becomes inefficient, eventually impossible. This threshold varies by organism. C4 plants can operate at lower carbon dioxide than C3 plants, but there's a hard limit. Below about 10 parts per million, even the most efficient photosynthesis fails. The model tracked when carbon dioxide would drop to these critical levels. Running these simulations required massive computing power. They ran thousands of iterations with slightly different starting parameters, different assumptions about volcanic outgassing rates, different assumptions about weathering efficiency, different assumptions about biological productivity. Each run followed Earth forward through time, tracking temperature, carbon dioxide levels, oxygen levels, looking for the point where oxygen production stops. And across all these runs, despite variation in details, the conclusion was consistent. Oxygen disappears in about 1 billion years, give or take a few 100 million depending on assumptions. But the timeline is robust. It's not sensitive to small changes in parameters. The physics drives the outcome. This kind of modeling represents a triumph of modern science. We can simulate planetary evolution over billion-year timescales. We can integrate geology, chemistry, biology, astronomy. We can make testable predictions about the far future. Not in detail. We can't predict specific events, but we can predict trends, overall trajectories, ultimate outcomes. This is powerful. It gives us insight into processes we can never directly observe. Earth won't lose its oxygen in our lifetimes, or our descendants' lifetimes for millions of generations. But we can know it will happen. We can understand why. We can see the mechanism. That's remarkable. That's science at its best. The implications for life elsewhere become even more interesting when you consider the diversity of stars. The Sun is a G-type star, yellow, medium-sized, medium temperature. But most stars in the galaxy are M dwarfs, red dwarfs, smaller, cooler, dimmer. These stars burn hydrogen much more slowly than the Sun. They last trillions of years instead of billions. They also increase brightness more slowly. A planet in the habitable zone of an M dwarf might maintain oxygen much longer than Earth. Perhaps 10 billion years instead of 1 billion. This would give life more time to evolve, more time for intelligence to emerge, more time for civilizations to develop. If complex life needs billions of years to evolve, M-dwarf planets might be better bets than G-dwarf planets. Despite other challenges like tidal locking and stellar flares, the extended habitability might compensate. Conversely, F-type stars are larger and hotter than the Sun. They burn brighter and evolve faster. A planet around an F-star might lose oxygen in only a few 100 million years. Not enough time for complex life to evolve. This suggests there's a sweet spot in stellar types. M-dwarfs might last too long, but pose other habitability challenges. F-stars burn out too fast. G and K stars are Goldilocks, are long enough for evolution, but not so slow that other factors dominate. This refines our search for life. We should focus on planets around G and K type stars, similar to the Sun or slightly cooler. Those systems offer the best balance of longevity and stability for complex life to emerge and flourish. The oxygen timeline also affects our thinking about the Fermi paradox. If intelligent civilizations are common, where are they? Why haven't we detected signals? Why haven't they visited? One answer might be timing. If oxygen-rich atmospheres last only 1 billion years or so, and complex life needs hundreds of millions of years to evolve intelligence, the window for technological civilizations is narrow, maybe only a few 100 million years on average. In a galaxy billions of years old, civilizations might be scattered across time. Most have already come and gone. Most haven't emerged yet. We might be in a relatively quiet period, looking for neighbors who don't exist yet or existed long ago. This doesn't solve the Fermi paradox completely, but it adds another constraint, another filter, another reason why contact might be rare even if life is common. There's also a psychological dimension to contemplating Earth's oxygen deadline. How does it make you feel? For some people, it's terrifying. The idea that Earth won't always be habitable. That complex life is temporary. That nothing lasts forever. This can trigger existential anxiety, Fear of death writ large, not personal death, but planetary death, species death, the end of everything we know. For others, it's liberating. If everything is temporary anyway, the pressure to achieve immortal significance disappears. You don't need to leave an eternal legacy. You just need to live well now. Make the most of your time. Enjoy the experience. Be kind. Be present. That's enough. Both reactions are valid. Both are human responses to confronting impermanence. Philosophers and theologians have grappled with impermanence for millennia. Buddhist philosophy centers on it. Anicca, the impermanence of all things. Nothing lasts. Everything changes. Clinging to permanence causes suffering. Accepting impermanence brings peace. Earth's oxygen timeline is Anicca on a planetary scale. Everything we know will change, will end. Fighting this reality is futile. Accepting it allows us to appreciate what we have while we have it, to find meaning in the temporary, to value experience over permanence. This isn't nihilism, it's realism, it's wisdom, and it's something science and ancient philosophy agree on. Nothing lasts, and that's okay. Western religious traditions often emphasize eternity, heaven, hell, souls, afterlife, permanence of the spiritual realm. But even in these traditions, Earth is temporary. The physical world is finite. There's an end times, an apocalypse, a judgment, then a new creation or eternal state. So even religions that promise eternal souls acknowledge that Earth is not forever. The oxygen timeline doesn't contradict this. It just specifies the mechanism and timeline. Earth becomes uninhabitable not from divine intervention, but from natural processes. The end comes not in fire and brimstone, but in rising temperatures and disappearing oxygen. But the fundamental insight is the same. This world is temporary. Act accordingly. Secular humanism finds meaning without appealing to the eternal. Life has value because it's the only life we know we have. Consciousness is precious because it's rare. Love matters because we experience it. Beauty is meaningful because we perceive it. None of this requires permanence. In fact, the temporariness enhances the value. If life lasted forever, it might feel less urgent, less precious. The finite nature of existence creates urgency, creates meaning, creates value. Earth's oxygen deadline is an extreme example of this finitude. Not just individual death, but planetary death. But the principle is the same. Things matter because they're temporary, because they won't last, because we have them now and won't always. Let's return to practical considerations. What does the oxygen timeline mean for space exploration? If Earth has a billion-year deadline, and if humanity wants to survive beyond that, we need to leave. Not tomorrow, not in 1,000 years, but eventually. This provides motivation for developing space technology, for establishing colonies on other worlds, for becoming a multi-planet species. Not because Earth is immediately threatened, but because long-term survival requires diversification, spreading across multiple planets, multiple star systems eventually, not putting all our eggs in one planetary basket. Current space exploration efforts are modest compared to what would be needed for interstellar colonization. We've sent humans to the moon. We've put robots on Mars. We have a space station in orbit. These are remarkable achievements, but they're local, within our solar system, within relatively easy reach. True long-term survival requires leaving the solar system, finding new stars, new planets, building the technology to travel between stars, to survive on worlds vastly different from Earth. to create new homes in alien environments. This is science fiction today, but it could be science fact in thousands or millions of years. If we survive that long, if we develop the necessary technology, if we maintain the will to explore and expand. The oxygen timeline gives us a clear deadline for leaving not Earth, but the Sun's aging system entirely. In about 1 billion years, Earth becomes uninhabitable. Mars might briefly become habitable as the Sun brightens. But that's temporary. Eventually, the entire inner solar system becomes too hot. The outer solar system offers possibilities. Europa, Enceladus, Titan. These moons might become habitable as ice melts and subsurface oceans warm. But, again, it's temporary. And living on icy moons has its own challenges. Limited sunlight, radiation from Jupiter and Saturn, no magnetic field protection. These aren't ideal long-term homes. Better than nothing, but not solutions for millions of years. Real long-term survival means leaving, finding new stars, young stars, G or K type stars with plenty of fuel left. With planets in stable orbits in habitable zones, building new civilizations around new suns. That's the long-term plan if humanity aims for true longevity. This sounds ambitious to the point of absurdity. We can barely put people on the moon. How could we possibly travel between stars, build civilizations around other suns? The answer is time. 1 billion years is an enormous amount of time. Modern humans have existed for about 300,000 years. Civilization for about 10,000 years. Industrial technology for about 200 years. Space technology for about 70 years. Imagine what we might accomplish in another 1,000 years. Another 1,000,000 years. Another 1 billion years if we survive. Technology advances exponentially in some domains. What seems impossible today becomes routine tomorrow. Flight was impossible until it wasn't. Space travel was impossible until it wasn't. Computers were impossible until they weren't. Interstellar travel is impossible now, but given enough time and motivation, maybe it won't be. Maybe our distant descendants will look back on our era and marvel at how limited we were, how small our ambitions, how confined to one planet. They'll live among the stars, travel between worlds as easily as we travel between cities, and they'll remember Earth as humanity's birthplace, the cradle, the place where it all started. But not home anymore, just history. Or maybe not. Maybe humanity goes extinct long before the oxygen crisis. Maybe we destroy ourselves. Climate change, nuclear war, pandemic, AI catastrophe. There are many ways we could fail. Many paths to extinction that are much nearer term than 1 billion years. The oxygen timeline assumes humanity or some successor species survives that long. That's a big assumption. Most species last a few million years before going extinct. Humans, as a species, are very young. We might not last. And if we don't, the oxygen timeline becomes academic. Interesting scientifically, but not personally relevant. Earth will lose its oxygen, whether we're here to see it or not. But let's be optimistic. Let's assume humanity survives, adapts, evolves, spreads, becomes something greater than we are now. In that scenario, the oxygen timeline becomes a milestone, a waypoint, a marker in humanity's long journey. Earth was home for billions of years. Our ancestors evolved here. Our civilization emerged here. But eventually we left, moved on. Found new homes, and Earth returned to its natural state. Oxygen disappeared, complex life ended, bacteria reclaimed the planet, and far away on distant worlds, humans remembered, told stories, preserved records, Earth, the homeworld, the place where we came from, the place we can never return to, not because it was destroyed, but because it changed, became something else, moved on just as we moved on. That would be a bittersweet but beautiful story, a proper ending to Earth's chapter in humanity's history. The study of Earth's oxygen deadline is ultimately about understanding our place in the cosmos. We're not eternal. Our planet is not eternal. The conditions that allow us to exist are not eternal. Everything is temporary. Everything changes. Everything ends. This is the fundamental truth of existence. And rather than being depressing, it can be empowering. It can free us from impossible expectations, from the burden of achieving permanence, from the anxiety of trying to make things last forever. Nothing lasts forever. So we don't have to. We just have to live well now. Appreciate what we have. Be kind. Be curious. Be present. Make the most of this extraordinary moment when Earth has oxygen and life and consciousness. When we can look up at the stars and wonder. When we can understand our place in the universe. When we can marvel at the temporary masterpiece of a living planet. That's enough. That's everything. That's the gift. Not permanence, but presence. Not eternity, but now. There's another dimension to this story that deserves attention, and that's how the oxygen timeline intersects with other aspects of Earth's future evolution. The disappearance of oxygen doesn't happen in isolation. It's part of a cascade of changes affecting every aspect of the planet. Let's walk through what else is happening during that billion-year countdown, because understanding the full picture makes the transformation even more profound. As the sun brightens and Earth heats up, the first casualty isn't oxygen, it's biodiversity. Species begin going extinct, not because they run out of oxygen, but because their habitats disappear. Rising temperatures change climate patterns. Rainfall shifts. Some regions that were wet become dry. Others that were temperate become too hot. Plants that evolved for certain conditions find those conditions gone. They can't migrate fast enough. They die out, and when plants go, the animals that depend on them follow. Ecosystems collapse from the bottom up. Coral reefs die first. They're already stressed by current ocean warming. As temperatures continue rising, even the most resilient corals bleach and die. Coral reefs support enormous biodiversity, thousands of species living in and around reef structures. When reefs die, this diversity crashes. Ocean ecosystems become simpler, less productive, less vibrant. Then rainforests follow. They need consistent rainfall and moderate temperatures. As climate patterns shift and temperatures rise, rainforest zones shrink. Trees die. The canopy opens. Sun penetrates. The understory dries out. Forest becomes savanna. Savanna becomes grassland. Grassland becomes desert. The Amazon, the Congo, Southeast Asian rainforests, all gone, replaced by arid scrubland or barren desert, and with them go thousands of species found nowhere else. Unique evolutionary lineages, millions of years of adaptation, all erased by rising temperatures. Polar regions warm fastest. This is already happening today. The Arctic is heating twice as fast as the global average. As temperatures continue rising over geological timescales, ice disappears completely. Not just seasonal ice, but permanent ice caps, glaciers, ice sheets, all gone. The Arctic Ocean becomes open water. Antarctica becomes rocky islands. Species that depend on ice, polar bears, penguins, seals, have nowhere to go. They go extinct, And the loss of ice has cascading effects. White ice reflects sunlight, dark water and rock absorb it. This accelerates warming, a positive feedback loop. The planet heats faster because the reflective ice is gone. This is called albedo feedback. It's one of many feedbacks that amplify change, making the transformation faster and more severe than it would otherwise be. The oceans themselves undergo dramatic changes. As water warms, it holds less dissolved oxygen. This is happening now and will continue. Warmer water means less oxygen available for marine life. Fish and other organisms that depend on dissolved oxygen suffer. Some species adapt by moving to cooler, deeper waters. But there's a limit. Eventually, even the deep ocean warms. And some organisms can't adapt. They go extinct. The ocean also becomes more acidic as it absorbs carbon dioxide. This affects shell-building organisms, corals, mollusks, plankton with calcium carbonate shells. The shells dissolve in acidic water. These organisms struggle. Many die out. The entire marine food web, which depends on plankton as the base, becomes unstable, simplified, less productive. On land, soil degrades. Soil is a living system. It contains organic matter from decomposed plants and animals, bacteria and fungi that break down this organic matter, nutrients that plants need, soil structure that holds water and allows roots to penetrate. But soil depends on continuous input of organic matter from plants. As plants die out due to heat and drought and low carbon dioxide, organic matter input declines. Soil microbes consume what's left. Without replacement, soil becomes sterile. Just mineral particles, sand and silt. No organic content, no structure, no nutrients. This accelerates desertification. Even if rain falls, it runs off the degraded soil without soaking in. Nothing grows. The land becomes a desert, not just from lack of rain, but from loss of soil quality. Rivers and lakes dry up. As temperatures rise, evaporation increases. More water leaves the surface, less stays in rivers and lakes. At the same time, precipitation patterns change. Some regions get less rain. Rivers that once flowed year-round become seasonal, then dry up completely. Their beds cracked and empty. Lakes shrink, become salty as water evaporates and leaves minerals behind. Eventually evaporate entirely, leaving salt flats, white expanses of crystallized minerals. No life, just salt. This is already happening to some lakes today. The Aral Sea, Lake Chad. Climate change and water diversion have shrunk them dramatically. Over geological time, this becomes the norm. Most inland water bodies disappear. The atmosphere itself changes chemically in ways beyond just oxygen loss. Methane levels rise as anaerobic bacteria flourish. Methane is produced by methanogens in oxygen-free environments, wetlands, ocean sediments, the guts of animals. As oxygen disappears, these environments expand. Methanogens thrive, pump methane into the atmosphere. Methane is a powerful greenhouse gas, much stronger than carbon dioxide at trapping heat. Rising methane levels accelerate warming, create a positive feedback. More heat means more methane, which means more heat. The atmosphere also accumulates hydrogen sulfide from sulfur bacteria. This gives the air a rotten egg smell. Toxic to us, but normal for the anaerobic world. The sky color changes. Scattering of light through a methane-rich atmosphere creates different colors than our familiar blue. Perhaps orange or brown, hazy, murky, not the clear blue we know. Magnetic field changes might also occur. Earth's magnetic field is generated by convection in the liquid iron outer core. This convection is driven by heat from the solid inner core and from radioactive decay. Over billions of years, Earth cools. Eventually, the outer core might solidify. When that happens, the magnetic field shuts off. Without a magnetic field, Earth becomes vulnerable to solar wind. Charged particles from the sun strip away atmosphere. This is what happened to Mars. If Earth loses its magnetic field before the oxygen crisis, it accelerates atmospheric loss. Oxygen disappears faster. The planet becomes inhospitable sooner. We don't know exactly when Earth's magnetic field will shut off. Maybe in a few billion years, maybe longer. But it's another factor in the equation, another system that won't last forever. Tectonic activity also declines over time. Plate tectonics is driven by heat from Earth's interior. Convection in the mantle moves plates, creates earthquakes, builds mountains, causes volcanism. But as Earth cools, convection slows. Plate movement slows, eventually stops. When this happens, volcanism declines. No more new mountains, no more volcanic eruptions releasing carbon dioxide. The carbon cycle breaks down. Without volcanic inputs, carbon dioxide levels drop even faster. This might happen before the oxygen crisis, or during it, or after. The timeline is uncertain, but eventually Earth becomes geologically dead. No plate tectonics, no volcanism, no earthquakes. A static, dead planet. Just rock and atmosphere, and no internal activity. Like Mars, frozen solid below a thin crust. All of these changes are connected, interrelated. Each affects the others. Rising temperature drives oxygen loss, but also drives biodiversity loss and ocean acidification and soil degradation. Methane rise amplifies warming, which accelerates everything else. Magnetic field loss accelerates atmospheric loss. Tectonic shutdown cuts off carbon dioxide replenishment. It's a cascade, a chain reaction, and once it starts, it's irreversible. You can't restart plate tectonics. You can't rebuild soil on a global scale. You can't bring back extinct species. These changes are permanent. They transform Earth from a living, dynamic, complex world into a simple, static, dead one, and the oxygen crisis is just one part of this larger transformation. The most visible part for us because we need oxygen, but not the only part. The whole planet is changing, dying, moving toward its final state. Understanding this complete picture is important because it shows how interconnected planetary systems are. You can't just look at oxygen. You have to look at temperature and biodiversity and oceans and soil and tectonics and magnetic fields. Everything together. Earth is a system. Change one part and everything changes. This is why planetary science is so complex. Why predictions are difficult, why we need sophisticated models that integrate multiple disciplines. And it's why Earth's habitability is so remarkable. All of these systems have to work together, be in balance, for complex life to exist, and that balance is temporary. Eventually, the systems drift out of balance, and habitability ends. This also explains why we're unlikely to find many Earth-like planets, not just planets in habitable zones, but planets at the right stage of evolution, with all systems in balance, with oxygen in the atmosphere, with biodiversity and soil and oceans and magnetic fields and active tectonics, all at the same time. This requires so many things to be right simultaneously. It's rare, not impossible. The universe is vast, but rare enough that we shouldn't expect to find Earth twins around every star. Most planets will be at different stages. Some too young, oxygen hasn't built up yet. Some too old, Oxygen is gone. Some never developed life, so never had oxygen. Some lost their magnetic field early and became Mars-like. Some are too close to their star and became Venus-like. The combination of factors that makes Earth habitable right now is special. Not unique necessarily, but uncommon and temporary. This realization has profound implications for how we value Earth. It's not just a planet, it's a rare configuration of systems in temporary balance, a moment in planetary evolution when everything aligns just right for complex life, for consciousness, for us. That moment won't last forever, but it's happening now. We're living in it, experiencing it. And that makes Earth not just our home, but a treasure, a jewel, a 1 in billions occurrence, at least in our local region of space. Maybe elsewhere in the galaxy, planets are going through their Earth-like phases, their oxygen-rich moments, their windows of complex life. We might be one of thousands or millions. But even if that's true, even if Earth-like planets are common, each one is temporary. Each has its moment. And then it passes. Earth's moment is now. And knowing that should change how we treat it, how we value it, how we protect it. The oxygen timeline is also a reminder of scale, geological scale, astronomical scale, scale beyond human comprehension. 1 billion years is longer than we can truly grasp. It's longer than life has been complex, longer than the entire history of animals. If you compressed all of human civilization into 1 second, Earth's remaining oxygen-rich time would be about 8 days. If you compressed Earth's entire history into 1 year, complex life appears in mid-September. Oxygen disappears in late August next year. We're living in late September right now, a brief autumn before the long winter. These comparisons help, but they still don't convey the reality. Deep time is deep, incomprehensibly deep. And learning to think at these scales changes your perspective on everything. Your life, your problems, your ambitions. They're so small in the context of deep time, so brief, so temporary, not unimportant, but contextual, limited, finite, and yet, paradoxically, this makes them more important, not less, because temporary things are precious precisely because they don't last. If your life was eternal, would it feel urgent? Would moments feel important? Or would they blend together in an infinite sequence? The finitude creates value, creates meaning, creates urgency. Every day matters because you don't have infinite days. Every breath matters because someday you won't breathe anymore. Earth's oxygen matters because someday it won't be there. This isn't depressing. It's clarifying. It focuses attention on what truly matters. Now. This moment, this experience, this breath, that's where meaning lives. Not in the infinite future, but in the finite present. Thank you for exploring Earth's oxygen deadline with me. If this journey into deep time expanded your sense of wonder at the moment we're living in, a like or subscribe really helps the channel keep investigating these profound questions. And remember, you're breathing oxygen right now. Your lungs are extracting it from air that won't always be there. The planet beneath your feet won't always sustain life like this. Everything you see, every tree, every cloud, every breath is part of a temporary masterpiece, a living world in its prime. Someday, far in the future, that will end. But it exists now, and that's the miracle. That's the gift. Not permanence, presence, not eternity. This moment. Good night, and may you never take another breath for granted.